Today, we're diving into the testing and commissioning of the electrical grid, focusing on Substation Automation Systems, or SAS, as part of Training Module 17. This manual is designed to guide you through the essential processes to ensure a reliable and efficient electrical grid by 2026. Let's explore how these systems come together to keep our infrastructure running smoothly. Here we have the reference framework for testing and commissioning electrical grids. This slide lists key standards organizations like IEC, IEEE, ASTM, NEMA, ENSI, SIGER, ICA, and KEMA, each playing a crucial role in setting guidelines and practices. It's important to apply the most stringent approved requirement whenever there's a discrepancy between project specs, manufacturer instructions, or standards. Also, documenting the reference used on the test sheet is essential to ensure transparency and traceability for future reviewers. This approach guarantees that our commissioning process is both reliable and compliant with industry best practices. Here we have the reference schematic for testing and commissioning the electrical grid, specifically related to CM_P17-1. This serves as a prerequisite work instruction to begin the SAS commissioning process. The visual includes critical details such as automation logic, communication paths, device readiness, and the review of evidence. Use this schematic to confirm important aspects like test boundaries, asset tags, safety controls, instrument calibration, and the levels of witness required before progressing. This ensures a thorough and compliant commissioning process. Before starting SAS commissioning, it's crucial to confirm that all technical, safety, documentation, network, and hardware prerequisites are fully complete. We begin by ensuring that key documents like the approved SAS architecture, panel drawings, HMI functional descriptions, and software lists are available. Next, we verify that FAT records, technical manuals, hardware specs, and cybersecurity approvals are all in place. Physically, we inspect all relevant equipment including SAS panels, servers, network devices, and power supplies for readiness. Safety measures such as lockout/tagout procedures, PPE, grounding, and communication with the control room must also be confirmed. In addition, all test instruments and laptops need valid calibration, approved software, and controlled user credentials. If any items are missing, they should be recorded in a punch list with assigned owners and due dates. The prerequisite checklist must then be formally closed with witnesses from the client, commissioning, and operations teams. Only when all these criteria are met and approved can SAS commissioning begin. We document completion with signed checklists, documentation registers, readiness photos, and witness approvals. Finally, there is a hold point where witnesses confirm test boundaries, cybersecurity and access approvals, actual test results, alarm evidence, restoration status, and punch closure before sign-off, ensuring everything is verified and ready for the next phase. Here we have the CM_P17-2 schematic reference, focusing on Part 1 of testing and commissioning the electrical grid. This slide presents the SAS fiber-optic cable testing schematic, which is crucial for verifying automation logic, communication paths, and device readiness. Use this reference visual to confirm important details like test boundaries, asset tags, safety controls, instrument calibration, and witness levels. This ensures a thorough and reliable commissioning process, aligned with Commissioning Manual Number 17 to 2.1. On this slide, we focus on the SAS fiber-optic cable testing as part of commissioning the electrical grid. The main goal here is to verify that all fiber-optic links are correctly routed, labeled, clean, and meet the approved insertion loss and continuity limits. We begin by confirming fiber link identification details such as source, destination, core number, cable type, length, and test direction from the approved cable schedule. Next, we thoroughly inspect all physical components like ODF, patch cords, connectors, and their routing to ensure they are in good condition and properly protected. Cleaning connectors properly is essential before referencing the optical light source and power meter to get accurate measurements. We then measure insertion loss for each fiber strand, recording critical parameters including wavelength and loss values. In cases where needed, an OTDR trace is performed to detect any splices or connector events and confirm there are no abnormal issues. All test results are compared against the specified loss budget and cable lengths, with any failed or marginal links marked for rework or retesting. Lastly, we restore the patching, replace caps and labels, and attach the instrument printouts, test results, and witness sign-off documentation. Remember, acceptance is only granted when labeling, routing, polarity, continuity, and loss results conform fully to the project's approved parameters. The entire testing process must also pass a hold point where the client, commissioning team, and operations witness verify all test boundaries, reference standards, cybersecurity, access approvals, and restoration status before final sign-off. This ensures the integrity and reliability of the SAS fiber network before moving forward. On this slide, we focus on the testing and commissioning of the electrical grid, specifically referencing the CM_P17-2 schematic, Part 2. This schematic covers the SAS fiber-optic cable testing and serves as a crucial visual guide for commissioning activities. Use it to verify the automation logic, communication paths, device readiness, and to gather the necessary evidence during the review. It's important to confirm key aspects like the test boundaries, asset tagging, safety controls, instrument calibration, and witness levels to ensure everything is in proper order. This process is detailed in Commissioning Manual Number 17 to 2.2, which should be your go-to reference for accurate and thorough commissioning steps. Here we focus on the SAS fiber-optic cable testing, Part 2, which is essential for ensuring the electrical grid's communication integrity. The key objective here is to verify that all fiber-optic links are properly routed, clearly labeled, clean, and within the approved insertion loss and continuity limits. We start by confirming the fiber link details from the cable schedule, including the ID, source and destination, core number, cable type, length, and test direction. Next, we thoroughly inspect all components like patch panels, patch cords, bend radii, connectors, and label conditions to ensure everything meets mechanical and routing standards. Cleaning connectors follows, along with calibrating the optical light source and power meter using approved reference cords. Then, we measure insertion loss on each fiber strand, recording key data such as wavelength, launch level, and receive level. If necessary, an OTDR trace is performed to detect any splice or connector issues and confirm there are no breaks or abnormal attenuations. Results are compared to the loss budget and cable length. Any link not meeting criteria is flagged for rework and retesting. Finally, the system is restored to its original state with proper patching, caps, and labeling, while attaching all test documents, instrument printouts, and obtaining the required witness sign-off. Acceptance requires that all labeling, routing, polarity, continuity, and loss results meet the project's approved specifications. For documentation, we compile comprehensive test sheets, OPM/OLS readings, OTDR traces if used, link schedules, photos, and records of any retests with sign-off for evidence. Before closing, a critical hold point ensures the client, commissioning team, or operations witness verifies test boundaries, references, cybersecurity, access, and final results, including alarms and restoration status, providing official approval before sign-off. This structured approach assures quality and reliability in the fiber-optic network testing process. Here we have the schematic reference for Part 3 of the CM_P17-2 series, focusing on testing and commissioning the electrical grid. This visual plays a crucial role during SAS fiber-optic cable testing, covering automation logic, communication paths, device readiness, and evidence review. Use this schematic as your guide to confirm important aspects like test boundaries, asset tagging, safety controls, instrument calibration, and the required witness levels. It's a comprehensive reference to ensure everything is thoroughly checked and documented as per Commissioning Manual Number 17 to 2.3. Here we focus on the SAS fiber-optic cable testing as part of the electrical grid commissioning process. First, it's crucial to verify that the fiber-optic links are properly routed, labeled, clean, and meet the approved insertion loss and continuity limits. We follow a detailed testing script starting with confirming the fiber link ID, source, destination, core number, cable type, length, and test direction from the cable schedule. Next, we inspect the optical distribution frame, patch cords, bend radius, connectors, tray routing, labels, and mechanical protection to ensure everything is in optimal condition. Connectors must be thoroughly cleaned before referencing the optical light source and power meter with approved cords. Then, we measure the insertion loss for each fiber strand, carefully recording all relevant data such as wavelength, launch level, receive level, loss, and test direction. If required, An OTDR trace helps identify splice or connector events, confirming there are no abnormal losses or breaks. We then compare the results with the specified loss budget and cable length, flagging any marginal or failed links for rework or retesting. Finally, patching is restored, caps and labels replaced, and all documentation including instrument printouts, result sheets, and witness sign-offs are attached. Acceptance is only granted when all labeling, routing, polarity, continuity, and loss criteria meet the approved project specifications. The complete evidence package includes fiber test sheets, OPM and OLS readings, OTDR traces if applicable, link schedules, photos, retest records for any failed links, and the critical witness sign-off. This process ensures we maintain strict control and quality in the commissioning phase. On this slide, we focus on the testing and commissioning of the electrical grid, specifically using the CM_P17-3 schematic as our visual reference. This schematic is crucial for the SAS function check of all peripheral devices, ensuring each component is operating correctly. It guides us through automation logic, communication paths, device readiness, and the review of evidence, providing a comprehensive overview during commissioning. Additionally, this visual helps confirm important aspects like test boundaries, asset tags, safety controls, instrument calibration, and the appropriate witness level, all of which are essential for a successful and safe commissioning process. On this slide, we focus on the SAS function check for all peripheral devices during the testing and commissioning of the electrical grid. The key objective here is to verify that each SAS peripheral device is properly installed, powered, connected, addressed, fully functional, and correctly visible on the SAS platform. We start by confirming the peripheral device list, tags, addresses, power supplies, ports, and wiring against approved drawings. Then we inspect the physical installation, including earthing, cable dressing, labeling, and panel cleanliness. Next, we check device communication with the SAS server and HMI, verifying online and alarm statuses along with correct device naming. Further steps include simulating or operating each input and output within approved boundaries, ensuring local indications, SAS displays, and event logs respond appropriately. We also test device status after power cycles to confirm there's no configuration loss. Any failures, missing labels, or incorrect addresses are documented as defects for correction. Finally, all devices must be restored to normal mode and show a healthy status before the witness closeout. Devices are accepted only when their tags, connections, addresses, online status, functional responses, and event visibility align with approved documentation. The evidence package includes checklists, screenshots, simulation records, defect logs, photos, and the witness sign-off. A critical hold point requires client, commissioning, and operations witness approval to confirm the test boundary, references, cybersecurity, actual results, and restoration before sign-off. This comprehensive process ensures every peripheral device is reliably integrated into the SAS platform. Here we have the CM_P17-4 schematic reference for testing and commissioning the electrical grid, specifically focused on SAS measurement testing. This visual is crucial as it serves as a reference for commissioning, covering automation logic, communication pathways, device readiness, and evidence review. Make sure to use it to confirm key aspects like the test boundaries, asset tags, safety controls, instrument calibration, and the required witness level. This ensures that every step in the commissioning process meets our standards and is thoroughly validated. This slide covers the SAS measurement testing process for verifying that injected analog values at the BCU and SAS measurement terminals are accurately displayed across the system. The goal here is to prove that values shown on the BCU, HMI, and SCADA match within acceptable accuracy. We start by confirming all measurement point details like ID, CT/VT ratio, engineering units, scaling, polarity, and phase reference, ensuring we work within an approved injection boundary. Safety is critical, so applying LOTO and isolating live circuits or using approved test points is mandatory. Never open CT secondary circuits. Next, we connect a calibrated secondary injection kit, verify wiring with reference schematics, and inject approved voltage or current values for each phase. We then confirm those values on the BCU, HMI, and SCADA systems, checking phase and sequence displays. Each injected value is recorded along with its displayed counterpart, deviation, timestamp, and measurement status to ensure traceability. We also verify operation under 0, normal, and selected range values, confirming alarms and quality flags function correctly. After testing, we remove injections, restore terminals, and confirm the system returns to live measurement and normal status. The acceptance criteria demand correct scaling, phase, polarity, units, accuracy, and display mapping across all platforms. Finally, all results are documented with test sheets, injection settings, screenshots, deviation calculations, instrument certificates, and witness sign-offs. The hold point requires client, commissioning, or operations witnesses to validate the test boundary, references, cybersecurity, actual results, alarms, restoration status, and punch list closure before sign-off. This thorough process ensures reliable and accurate measurement verification for safe operation. Here we have a key schematic reference for testing and commissioning the electrical grid, specifically focused on the SAS engineering workstation testing process. This visual serves as an essential guide for confirming several critical elements during commissioning. It helps verify the test boundaries, asset tags, safety controls, instrument calibration, and witness levels. By using this schematic, we can ensure that automation logic, communication paths, device readiness, and evidence reviews are all thoroughly checked and documented according to Commissioning Manual 17 to 5.1. This step is crucial to maintain system integrity and operational safety before going live. Here we focus on the testing and commissioning of the SAS Engineering Workstation, or EWS, which is a critical component in the electrical grid system. The main goal here is to thoroughly verify the hardware specifications, software integrity, access rights, and communication settings of the workstation. We'll start by checking the physical hardware, things like CPU, RAM, disk, network cards, and peripherals, including the UPS supply if applicable. Next, we confirm the software environment by verifying the operating system version, engineering software legitimacy, license status, antivirus updates, patch levels, local time accuracy, and user access roles. Then we move on to network configurations to ensure the EWS is correctly set up with the right VLAN, subnet, gateway, no IP conflicts, and stable communication with SAS servers and devices. We also validate the engineering tools, checking the project database and configuration files, ensuring the online connection and proper access privileges are in place. Backup functions are tested next, including export, restoration, and upload controls from approved locations. Cybersecurity measures are verified by reviewing event access, log retention, and controls on removable media and admin rights. Throughout this process, we document everything: screenshots, software versions, account roles, and connection statuses before seeking witness approval. For acceptance, the EWS must meet all hardware and software specifications, have fully licensed tools, healthy communication paths, and governed access and backup controls. Finally, a hold point requires client or commissioning team witness to confirm all tests, security aspects, and documentation before signing off and moving forward. Here we have the CM_P17-5 schematic reference, Part 2, focused on testing and commissioning the electrical grid. This visual serves as a crucial tool for SAS commissioning, showing automation logic, communication paths, device readiness, and evidence review. Use this schematic to confirm the test boundaries, verify asset tags, ensure safety controls are in place, check instrument calibration, and assess the required witness level. This is all detailed in Commissioning Manual number 17 to 5.2, providing clear guidance for a thorough and safe commissioning process. On this slide, we focus on the SAS Engineering Workstation testing, Part 2 of the commissioning process for the electrical grid. The main goal here is to thoroughly verify the engineering workstation hardware, access rights, engineering software, communication ports, configuration tools, backup and restore functions, and security controls. We start by checking the hardware specifications including CPU, RAM, disk space, and network cards, ensuring peripherals like monitor, keyboard, mouse, and UPS supply are all in order. Next, we verify the operating system details, software versions, license status, antivirus and patch levels, as well as local time and user access roles. Then, it's critical to confirm network settings, such as VLANs, IP addresses, and communication with SAS servers and IEDs. After that, we open the approved engineering tools to check project databases, configuration files, and access privileges for read or write permissions. We also test backup and export functions, ensuring configurations can be uploaded, downloaded, or restored from approved backups. The process continues with verifying event and alarm access controls, log retention, and cybersecurity restrictions, especially for removable media and administrative accounts. Throughout the testing, we record screenshots, software versions, user roles, and connection statuses to provide clear evidence before gaining witness approval. The acceptance criteria require that hardware and software specifications match, license tools operate correctly, communication paths are stable, and access and backup controls are properly managed. The evidence package includes checklists, screenshots, network and backup confirmations, access matrices, and sign-offs. Finally, there is a critical hold point where client, commissioning, or operations witnesses confirm all test boundaries, cybersecurity measures, actual results, and restoration states before giving the final approval. This ensures everything is fully verified and compliant before moving forward. Here we have the CM_P17-6 schematic reference, specifically focused on testing and commissioning the electrical grid using SAS Ethernet switches. This visual serves as a comprehensive guide for commissioning, covering automation logic, communication paths, device readiness, and evidence review. It's essential to use this schematic to verify the test boundaries, ensure asset tags are correct, confirm safety controls, check instrument calibration, and determine the appropriate witness level. This ensures a thorough and accurate commissioning process, aligned with Commissioning Manual number 17-6. Here we have the testing and commissioning process for SAS Ethernet switches within the electrical grid. The key goal is to verify that these switches are installed correctly and functioning according to the approved architecture. We start by confirming all physical aspects: the switch tag, location, power supply, grounding, port labels, and firmware versions. Then, we move on to checking the network settings, such as management IP, hostname, VLAN configurations, and other protocols like SNMP and NTP. Next, the port status is checked against the approved port map to ensure all connections to servers, HMIs, gateways, and other devices are correct. Communication tests follow, using ping and link status tools to verify data flow and link integrity. We also verify redundancy features, alarm contacts, power supply alarms, and overall switch health status to the supervisory systems. After successful tests, the as-left configuration is backed up and any deviations are documented. Finally, the network topology is restored, ensuring no critical alarms or disabled ports remain. The acceptance criteria state that switches are accepted only when installation, configuration, redundancy, alarms, and backup records fully comply with the approved design. The evidence package includes checklists, configuration backups, communication test records, alarm screenshots, and witness sign-offs. Importantly, there is a hold point for client, commissioning, and operations teams to review and confirm all test boundaries, references, cybersecurity, actual results, and restoration status before final sign-off. This ensures thorough quality control and accountability throughout the commissioning process. Here we have the CM_P17-7 schematic reference for testing and commissioning the electrical grid. This visual is essential for confirming the SAS redundancy testing process. It clearly outlines the commissioning steps, including automation logic, communication pathways, device readiness, and evidence review. Use this schematic to verify test boundaries, asset tags, safety controls, instrument calibration, and the appropriate witness levels. It serves as a comprehensive guide in line with Commissioning Manual number 17-7 to ensure everything operates safely and efficiently. Here we have the SAS redundancy testing, which is crucial to ensure that all redundant components like servers, workstations, LAN paths, gateways, and operator functions operate correctly during planned failure simulations. The test follows a detailed procedure starting with confirming the redundancy topology, including active and standby servers and all relevant connections. Next, we record the normal baseline status to have a reference point. Then, we simulate an approved failure of one component while making sure there's no unsafe control impact. During this, we verify automatic switchover, client reconnection, data continuity, and operator visibility. After that, the failed component is restored and resynchronization is checked. We repeat this for all redundancy paths and record critical data like switchover times and operator impact. The test concludes by confirming normal topology, backing up configurations, and obtaining witness approval. The acceptance criteria require that loss of a single approved component does not disrupt operator control beyond set limits, and that recovery is fully documented. All evidence, including test sheets, screenshots, event logs, and witness sign-offs, are compiled into the final package. A hold point ensures that all stakeholders verify the test boundary, cybersecurity compliance, actual results, and restoration status before sign-off. This thorough process guarantees system reliability and operational safety. On this slide, we focus on the CM_P17-8 schematic reference, which is central to testing and commissioning the electrical grid. This visual outlines the SAS Gateway's testing schematic, providing a clear guide for commissioning by showing automation logic, communication paths, device readiness, and evidence review. This reference is crucial for confirming test boundaries, asset tags, safety controls, instrument calibration, and witness levels during commissioning. Use the commissioning manual number 17 to 8 alongside this schematic to ensure thorough and accurate testing procedures. Here we have the SAS Gateway's testing process, an essential part of testing and commissioning the electrical grid. The main goal here is to verify that the gateway hardware, protocol mapping, and communication between the SAS and both upstream and downstream systems are functioning correctly, ensuring accurate data transfer to external control centers. To carry out this testing, we use several instruments and equipment, including a gateway workstation, protocol analyzer, ping tool, test leads for serial and Ethernet connections, an approved mapping table, and tools like the HMI/SCADA display along with an event log viewer. The step-by-step testing script begins by confirming the gateway hardware specifications such as power supply, network and serial ports, IP address, protocol settings, and approved mapping tables. Next, we verify communication to SAS servers and HMI, as well as to upstream SCADA or NCC systems in accordance with the approved architecture. Then, we check data mapping for different data types, including analog signals, status, alarms, command feedback, and quality flags, all against the approved signal list. Following that, we simulate selected signals to verify the gateway's transfer accuracy, HMI/SCADA display, timestamp correctness, quality flags, and event logs. The testing continues by examining communication loss and recovery behavior, confirming alarms, reconnection capabilities, and data recovery functions. We also back up the gateway configuration, documenting firmware and software versions, IP settings, and protocol parameters. Finally, we restore normal communication and confirm that no stale values, communication faults, or mapping mismatches remain. The acceptance criteria require that hardware, protocol configuration, mapping, timestamps, quality, and loss/recovery behaviors strictly meet the approved interface requirements. The result and evidence package includes all relevant documentation such as the gateway checklist, mapping verification sheets, protocol screenshots and logs, SCADA/HMI screenshots, configuration backups, and the witness sign-off. Before sign-off, there is a critical hold point where the client, commissioning team, and operations witness confirm the test boundaries, references, cybersecurity and access approvals, actual results, alarm and sequence of events evidence, restoration state, and punch list closure to ensure everything is properly validated. This thorough process guarantees that the SAS gateway operates reliably within the electrical grid's control system. Here we have the CM_P17-9 schematic reference, which is a crucial tool for testing and commissioning the electrical grid. This visual guide plays a key role in SAS commissioning by illustrating automation logic, communication pathways, device readiness, and evidence review. Make sure to use it to confirm important aspects like test boundaries, asset tags, safety controls, instrument calibration, and the required witness level. This ensures a thorough and compliant commissioning process according to Commissioning Manual number 17-9. Here we have the CM_P17-9 test script focused on SAS GPS testing as part of the testing and commissioning of the electrical grid. The primary goal here is to verify the GPS clock hardware, antenna signal, time distribution, synchronization status, and ensure correct timestamps across SAS devices and SOE records. We start by inspecting the GPS clock, antenna, cabling, and related components against approved drawings. Next, we verify the GPS lock status, satellite connection, time zone, and output format like NTP, PTP, or IRIG-B if applicable. Then, we check the synchronization status on servers, gateways, and other devices. We continue by generating or simulating events to confirm accurate timestamp sequences across HMI, SOE, and SCADA displays. We also simulate loss of GPS signal to observe holdover behavior, alarms, and recovery. All configuration data, alarm status, and any time drift are carefully recorded. Finally, we restore the GPS lock state and verify that no alarms remain. Acceptance requires all SAS devices to synchronize perfectly with the approved time source, ensuring all event timestamps are accurate and traceable. Documentation includes test sheets, screenshots, event comparisons, and witness sign-off to close the verification process. This procedure ensures robust time synchronization essential for reliable grid operations. Here we have the schematic reference for testing and commissioning the electrical grid, specifically focusing on the SAS IED testing. This Part 1 visual is crucial for confirming several critical elements during commissioning. You'll use it to verify the test boundary, asset tags, safety controls, instrument calibration, and witness levels. Additionally, it serves as a reference for automation logic, communication paths, device readiness, and evidence review. Make sure to consult this schematic closely as outlined in Commissioning Manual 17 to 10.1 to ensure a smooth and compliant commissioning process. On this slide, we're focusing on the SAS IED testing, Part 1, which is critical for commissioning the electrical grid. The key objective here is to thoroughly verify the intelligent electronic device's hardware, firmware, configuration, communication, and its functional inputs and outputs. We also check the device's display handling and ensure that it correctly reports SAS events. First, we make sure that the IEDs identification details like tag, bay association, model, firmware version, and communication addresses are all correct and match the approved documentation. Then we inspect the wiring, power supplies, grounding, terminal connections, as well as communication links and panel mounting for physical correctness. Next, the device's operational status is checked, including its online connectivity, time synchronization, self-supervision features, and mapping between the HMI and SAS points. This step ensures the IED is properly integrated and communicating as intended. Following that, we inject or simulate analog and binary inputs to verify the device's display responses, output contacts, alarms, and event indications. We confirm all these functions behave according to specifications. We also verify the handling of displays, acknowledge and reset functions, access restrictions to settings, and the recording of faults and disturbances, which are essential for reliable fault analysis. After testing, test connections are restored to normal, events are cleared as approved, and the device status is confirmed to be normal, with no active alarms or test modes left in place. Throughout the process, detailed records of settings, versions, tested points, outputs, failures, corrective actions, and witness approvals are logged meticulously. The IED is accepted only when hardware, configuration, communication, and all functional behaviors conform strictly to approved requirements. Finally, the result package includes comprehensive test sheets, logs, screenshots, and a signed witness record to ensure accountability and traceability. The hold point ensures client, commissioning, and operations personnel confirm all aspects before final sign-off, including cybersecurity and access approvals. This approach guarantees that every detail is correctly validated before the IED is commissioned for operation. On this slide, we focus on testing and commissioning the electrical grid, specifically looking at the CM_P17-10 SAS IED testing schematic, Part 2. This visual is crucial as it serves as a reference for SAS commissioning, automation logic, communication paths, device readiness, and evidence review. Make sure to use it to confirm key elements like the test boundary, asset tags, safety controls, instrument calibration, and the required witness level. This ensures everything is aligned with the standards outlined in Commissioning Manual Number 17 to 10.2. Here we have the second part of the SAS IED testing script, which covers a comprehensive and step-by-step procedure to ensure the IED functions correctly within the electrical grid. First, we verify all essential IED details such as its tag, bay association, model, firmware version, and communication addresses. Then we inspect the physical setup, wiring, power supply, grounding, and all terminal connections. Next, we check the device's online status, confirm time synchronization, and review communication protocols alongside the HMI and SAS point mapping. Following that, we perform input injections or simulations to validate the IEDs display responses, output contacts, alarms, and event indications. We also test display handling features, including reset and acknowledge functions, access restrictions, and event or fault recording capabilities. After testing, all connections are restored, test events cleared, and the device's normal status confirmed without any active alarms. Throughout this process, detailed records must be kept, including settings, test points, screenshots, failures, corrective actions, and witness approvals. The IED is accepted only when hardware, configuration, communication, time sync, and mapping fully comply with approved requirements. Finally, the evidence package, including test sheets, logs, photos, and sign-offs, is compiled. A hold point ensures that client and commissioning teams review all results, cybersecurity measures, restorations, and punch list closures before final sign-off. This meticulous approach guarantees the IED's reliable operation in the grid. Here we have a key reference schematic from the commissioning manual, specifically CM_P17-11. This visual serves as an essential tool during testing and commissioning of the electrical grid. It covers several critical aspects such as automation logic, communication paths, and device readiness. Using this schematic helps us ensure that all test boundaries are clearly defined, assets are properly tagged, safety controls are in place, and instruments are calibrated accurately. Additionally, it guides us on the appropriate witness levels needed for verification. Overall, this is a vital resource to confirm everything is correctly set before moving forward. This slide focuses on the testing and commissioning process for the maintenance laptop used in electrical grid operations. The key objective here is to verify that the maintenance laptop can safely support SAS maintenance tasks without any risk of uncontrolled access, wrong software, malware, or configuration loss. We follow a detailed step-by-step script to ensure this. First, we check the laptop's asset ID, hardware specs, charger, and physical condition. Then, we verify approved software versions, licenses, antivirus status, and user account controls. Next, we confirm connectivity to the SAS device through approved interfaces, making sure production network security remains intact. We also open project files to verify read, view, backup, and diagnostic functions according to authorized roles. Exporting and backing up files is carefully tested along with storage location and media control. Disconnection procedures include logging out, malware control, and restoring network settings. Throughout, we document screenshots, software versions, access roles, backup names, and obtain witness approval. Acceptance hinges on approval of hardware, software, access, cybersecurity controls, and backup functions. All results are compiled in a comprehensive evidence package. Finally, a hold point requires client, commissioning, or operations witnesses to validate the entire test boundary, references, cybersecurity and access approvals, actual results, alarms, restoration state, and punch list closure before sign-off. This ensures the maintenance laptop meets rigorous safety and operational standards. Here we have the CM_P17-12 schematic reference, which is essential for testing and commissioning the electrical grid. This operating workstation testing schematic provides a clear visual guide for SAS commissioning, covering automation logic, communication pathways, device readiness, and evidence review. Use this schematic to confirm critical aspects such as test boundaries, asset tagging, safety controls, instrument calibration, and witness levels, ensuring a thorough and compliant commissioning process. This is all detailed in Commissioning Manual number 17-12 for your reference. This slide outlines the testing and commissioning process for the operating workstation in the electrical grid system. Our main goal here is to verify all aspects of the operator workstation, from hardware and software to alarm handling and security access. The references include engineering test formats and hardware specs to guide us. We use equipment like the operating workstation itself, operator accounts, HMI clients, and network tools to conduct the tests. The step-by-step script begins with checking the physical hardware and peripherals, then moves to verifying software versions, licenses, and user roles. We also confirm the workstation's online status and the availability of key displays like alarms and trend pages. Next, we simulate alarms to test their display, priority, and operator acknowledgement, ensuring navigation functions correctly. Operator controls are checked to allow authorized functions only, blocking unauthorized configurations. We test print and export functions and finally restore the system to normal, documenting everything thoroughly with screenshots. For acceptance, the workstation must meet all hardware and software requirements, including secure access and proper alarm management. The result package contains checklists, screenshots, permissions records, and a witness sign-off. A hold point requires approval from client, commissioning, and operations teams to confirm test boundaries, cybersecurity, and final restoration before we sign off on the process. Here we have the CM_P17-13 schematic reference, which is crucial for testing and commissioning the electrical grid. This visual provides comprehensive guidance for SAS panels inspection and testing, covering automation logic, communication paths, device readiness, and evidence review. Use it to confirm key elements like test boundaries, asset tags, safety controls, instrument calibration, and witness levels. This ensures that all processes adhere to the standards outlined in Commissioning Manual number 17-13. Here we have the comprehensive test script for SAS panels inspection and testing. The main goal is to ensure that these panels are physically complete, safe, properly labeled, powered, wired, grounded, ventilated, and fully prepared for functional automation testing. We rely on specific references, including approved panel schematics and hardware specifications, to guide the inspection process. Our toolkit includes an inspection checklist, multimeter, torque tools, label schedule, panel drawings, communication devices, and safety inspection records. The testing follows a clear step-by-step script. First, we confirm the panel tag location, drawing revision, vendor documents, nameplate, panel rating, and environmental suitability. Next, we thoroughly inspect the enclosure, door seals, gland plates, cable entry, earthing, segregation, terminal labels, ferrules, cable dressing, and spare cores. Then we verify the DC and AC supplies, status of MCBs and fuses, UPS feed, power supply outputs, auxiliary relays, switches, lamps, fans, and alarm contacts. We also check Ethernet and fiber patching, switch status, interfaces with gateways, servers, and IEDs, patch cord labels, and communication port allocation. Following that, we perform continuity and point-to-point checks for selected circuits and verify alarms or indications to the SAS when applicable. Any defects such as loose wires, missing labels, wrong ferrules, unapproved changes, or abnormal panel conditions must be promptly closed. Finally, we document everything by recording panel photos, test results, punch list closures, and confirming the final clean and closed panel status. The acceptance criteria require all installation quality aspects, power, grounding, labeling, wiring, communication, and selected functional checks to be complete and normal. All findings are compiled into a detailed evidence package, including the inspection checklist, continuity records, photos, alarm and communication screenshots, punch closure reports, and witness sign-off. Importantly, a hold point is established where the client, commissioning team, or operations witness must confirm key test boundaries, approve references, verify cybersecurity and access, review actual results and alarm evidence, ensure restoration state, and confirm punch closure before signing off. This thorough process guarantees the SAS panels meet all safety and operational standards before moving forward. Here we have the CM_P17-14 schematic reference for testing and commissioning the electrical grid, specifically focusing on the SAS servers. This visual is crucial because it shows the commissioning process, including automation logic, communication paths, device readiness, and the review of evidence. Use it as a guide to confirm important details like test boundaries, asset tags, safety controls, instrument calibration, and witness levels. It's all part of Commissioning Manual number 17-14, designed to ensure everything is thoroughly checked and verified. This slide outlines the comprehensive testing and commissioning process for SAS servers within the electrical grid. The main objective here is to verify that the SAS servers meet all hardware and software requirements, ensuring reliable operation of event logging and database functions. We begin by checking the server hardware specifications, including CPU, memory, storage, RAID configurations, power supplies, and network components. Next, we verify the operating system, software versions, license status, and ensure antivirus and patching are up to date along with time synchronization. Then, network settings are confirmed, such as hostname, IP address, VLANs, gateways, and communication with switches and clients. After that, we assess server application health by testing data acquisition, event logging, alarm processing, client connections, and report access. Backup and restore readiness are tested thoroughly, along with event export and storage capacity. If applicable, server redundancy or failover status is verified with the current active and standby conditions noted. Finally, we restore the server to normal service and confirm that no critical alarms remain. Acceptance is granted only when all hardware, software, services, communications, backups, and redundancy meet the approved criteria. The result package includes detailed test sheets, status screenshots, and records of all tests performed. We also have a critical hold point where client or commissioning personnel witness and approve the tests, confirm cybersecurity compliance, and validate all evidence before sign-off. This ensures thorough accountability and reliability before moving forward. On this slide, we focus on the testing and commissioning of the electrical grid, specifically highlighted by the CM_P17-15 SAS function testing schematic. This visual serves as a crucial reference during SAS commissioning, providing a clear view of automation logic, communication paths, device readiness, and evidence review. Use it to confirm key elements like test boundaries, asset tags, safety controls, instrument calibrations, and witness levels. This ensures thorough and accurate commissioning, supported by guidelines found in Commissioning Manual number 17-15. On this slide, we're focusing on the first part of the SAS function testing within the electrical grid testing and commissioning process. The goal here is to verify end-to-end SAS functions starting from field or IED simulation through to SAS processing, HMI and SCADA display, alarm and SOE records, and finally, operator response. We refer to the relevant documentation such as WI-NG 6460-002-007 and the SAS function check test format, along with the SAS cubicle drawing and approved signal list. We use instruments like multimeters, secondary injection kits, and simulators such as ASE 2000, plus tools for HMI, IED, and SLE viewing. The testing follows a clear step-by-step script. First, confirming all function, signal, and mapping lists, then setting safe test boundaries and notifying the control room. Next, simulating selected points and verifying object state, alarm priority, timestamps, and operator acknowledgement, followed by testing commands under approved conditions, checking function behavior after communication interruptions or device restarts, and finally, restoring all signals and alarms to their normal status. The acceptance criteria require that all tested signals and commands match the approved source, logic, displays, alarms, SOE records, and restoration requirements. All results must be documented through test sheets, traceability records, simulator logs, screenshots, and command proofs. Before sign-off, a hold point ensures client, commissioning, and operations witnesses confirm the test boundary, cybersecurity and access approvals, test results, alarm and SOE evidence, restoration state, and punch list closure. This thorough approach ensures the SAS functions operate reliably and safely as designed. Here we have the second part of the CM_P17-15 schematic reference, focusing on testing and commissioning the electrical grid. This visual is crucial for guiding the SAS function testing process. It details the commissioning steps, automation logic, communication pathways, and ensures the readiness of devices. Use it to verify key elements such as test boundaries, asset tags, safety controls, instrument calibration, and the level of witness required during testing. This comprehensive reference helps maintain accuracy and safety throughout the commissioning process. Let's review the SAS function testing procedure outlined in this script. First, we need to verify the entire end-to-end SAS functions, starting from field or IED simulation through SAS processing, all the way to HMI and SCADA displays, alarm and sequence of events records, and operator response. The reference documents include the WI-NG 6460-002-007, the SAS function check test format, cubicle drawings, architecture, and approved signal lists alongside the ASE 2000 simulator. For equipment, we'll use tools like the multimeter, secondary injection kit, ASE 2000 or equivalent simulator, HMI/EWS/OWS interfaces, IED tools, approved signal list, and SOE viewer. The testing script follows a clear sequence. We begin by confirming the function list, signal list, equipment tags, IED mapping, and alarm requirements. Next, we apply safe test boundaries and notify the control room before simulation. Then, simulate selected status and feedback points at the approved source or device boundary. Following that, we verify the HMI and SCADA object states, alarm priorities, event timestamps, value scaling, and operator acknowledgements. We also test selected command and feedback functions, checking permissives, blocking, and final indications under approved conditions. It's critical to verify how functions behave after communication interruptions, restorations, or device restarts when applicable. Finally, we restore all signals, commands, test modes, temporary accounts, and alarms to their normal as left status. For acceptance, all tested signals and commands must match approved sources, logic, displays, alarms, and restoration requirements. The results package should include the test sheet, signal traceability, simulator or injection records, screenshots, command proof, punch closures, and witness sign-offs. A hold point requires confirmation by the client, commissioning, and operations teams, verifying test boundaries, references, cybersecurity, actual results, alarm evidence, restoration state, and punch list closure before final sign-off. This ensures thorough and compliant commissioning of the electrical grid SAS functions. Here we have the overall interlocking testing schematic for the SAS system, referenced as CM_P17-16. This visual is essential for the commissioning process, as it highlights key aspects like automation logic, communication pathways, and device readiness. Use it as a guide to confirm your test boundaries, verify asset tags, and ensure all safety controls and instrument calibrations are properly in place. Additionally, it helps in reviewing witness levels to maintain compliance throughout the testing and commissioning of the electrical grid. On this final slide, we focus on the SAS overall interlocking testing, which ensures safe operation across all breakers, disconnectors, earthing switches, and bay logic. The key objective here is to prove that the interlocking system allows only safe operations and effectively blocks any unsafe commands. We follow a detailed step-by-step testing script, starting with confirming the interlock matrix, equipment status, and configuration settings. Then, we apply lockout-tagout procedures and notify relevant personnel before proceeding with testing. We set approved initial conditions, test permitted operations to verify correct command acceptance and feedback, and attempt blocked operations to confirm proper denial and alarm generation. It's vital to also check reset and normalization logic to ensure no bypass or abnormal status remains after scenarios. Acceptance criteria require that all safe operations are allowed, unsafe ones blocked, and every result documented with correct SOE and HMI evidence. The test results are compiled into a comprehensive evidence package, including command records, screenshots, and checklists. Finally, a hold point is established where client, commissioning, and operations teams review and confirm the test boundary, references, cybersecurity, and restoration state before signing off. This thorough process guarantees the electrical grid's interlocking system maintains the highest safety and reliability standards.